Welcome back to another session for Applied Thermodynamics. Today we are going to continue our discussion about the gas power cycles. In previous session, I have started to introduce you some basics about the gas power cycle. I told you that working fluid in this type of the cycles is air actually, or we assume it is air. And briefly, I told you what can be standards or the assumptions which we need to solve problem related to this type of the cycles. And I told you also why these cycles are important, because the cycles are being used to produce power, which is our main goal, to use different most of the equipment. I told you about the actual and ideal cycles, and I told you that ideal cycle is a cycle similar to the actual cycles. It is actually resemble the actual cycle, but it's we have some assumption to make the cycle easier to illustrate, easier to understand, and easier to evaluate. I discussed about the Carnot cycle, and I told you why it is important and how we can calculate its efficiency. And I told you that efficiency of Carnot cycle is only dependent on the temperature of the heat source and heat sink. Today we are going to continue our uh, discussion. I briefly will continue to discuss about Carnot cycle. Then I will tell you about air standard assumptions, and I will tell you why these assumptions are important. And okay, then I will tell you about air standard assumptions. I will tell you why these assumptions are important and why we need to use them and how we can use them actually. We will continue our discussion to introduce you reciprocating engines or internal combustion engines actually. I will tell you about why it is important. We will discuss about different properties of an mm, internal combustion engine, actually a piston cylinder device. And I will also tell you about the compression ratio, displacement volume, about the cycle which we have for this type of the engines, and also we will go through the different type of the uh, internal combustion engine. I mean, in terms of the combustion cycle, I will introduce you the Otto cycle, which is very important type of the cycle for the internal combustion engine, and we will use this cycle to describe the internal combustion engine, the gasoline type actually. I will tell you about four-stroke and two-stroke combustions, and I will tell you their difference. We go through the calculation. We will calculate the thermal efficiency of the Carnot cycle, the Otto cycle, which is actually the thermal efficiency of the gasoline engine. And finally, we will see how much is the maximum possible thermal efficiency of this type of cycle and how we can calculate it, how we can improve it, what are the parameters effective on this thermal efficiency actually. And finally, we will solve an example related to this type of the cycle. I mean Otto cycle, which is one type of the gas power cycle. So you can see what we will have for today's session in this slide. And this today topic is actually based on the field number one and field number two, or course objective number one and course objective number two. So in previous session, I told you about some idealization and simplification, which are important for us to solve different problems. Like these three assumptions, which are important to solve a problem about power cycles, actually. First of all, we need to assume that our cycle is frictionless. All of the processes actually in the cycle are frictionless. and also all of the process are happened or occurred in a quasi-equilibrium manner. And the third assumption, which we need to have for all or different type of the power cycle, is to assume the cycle is an adiabatic cycle, or we don't have a transfer through them, or we can assume that it is negligible. Today's session, I am going to continue and to tell you that what we have actually for a standard assumption. For different type of the uh, gas power cycles, you know what we mean. As I told you in first session, I told you about the gas power cycle, which in this type of the cycle, the working fluid remain a gas. This is important. This is actually the main characteristic of the gas power cycle. Why we call them? Because the working fluid remain a gas throughout the entire cycle. This type of the cycle actually are is common in spark ignition engines, diesel engines, conventional gas turbines. And in this chapter, we will consider all different types of these cycles. We will discuss about the spark ignition engines. We will discuss about diesel engine. I will introduce you the turbines and different cycles which we have in the turbines, the gas power cycle turbines actually. In all of these equipment actually, energy which we have to run that cycle, excuse me, I received the message. Rather, if you are in the class, you can just open your mic and ask your questions. Okay.
Okay, why they do not identify the attender?
Because I think your maybe your name is missed or dropped from the list, I will add your name. So please remind me at the end of the class, or because I will give you a break, short break. During that break, we can discuss about your attendance. I can add your name. Just remind me about that.
Okay, sir.
Okay, sorry, class. Uh, in all these type of the engines, I mean diesel engine, spark ignition engines, and turbines, we have a source of energy which comes from the burning of kind of the fuel. For example, you know, for your car, for example, you need to pour fuel in your car to work to produce energy. Because of that, we call this type of the engine as internal combustion engine, because combustion is happening, combustion reaction, the reaction of the fuel with the air is happening inside the chamber, inside the cylinder chamber. We call that, because of that, we call this internal combustion engines. And in this combustion process actually, we have combination of two different type of the fluid actually, air and fuel. So we have two different kind of the fuel which react in this cycle. So this is first, part which we have a complexity. First problem. As I said, for power cycle, we need to assume we have a gas throughout all cycle. But here we have fuel, and from one side and from the other side we have the air. So we have two kind of the fuel fluid actually, and one of them is not generally speaking gas. So how we can deal with this type of the cycle, we will see later. However, you know that most of the air is nitrogen, which does not react with any molecules in the fuel. So what we have actually in the combustion cycle is air, or we can assume we have air in the inside the cylinder. Why it is important later we will see, because when we are going to calculate, for example, the change in the energy, change in the enthalpy during the cycle, from thermodynamics we need to know the enthalpy, we need to know the uh, 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 energy, we need to know enthalpy, and so on. So, as you know, we have different methods to find enthalpy and entropy for a cycle. How we can find that for a state, especially, we need to go to the sum table. Okay, but we don't have those tables for all of the substances, or sometimes we need to use some complex equation to calculate U and H. But if we assume we have air, and actually as the ideal gas, then simply we can refer to the table for air as the ideal gas and find U, H, and then substitute in our equation. Then we can calculate the, for example, thermal efficiency of the cycle. How much energy is come to the system, to the cycle, Q in, how much energy go out, Q out. So this is first thing which may help us. However, in internal combustion cycle, later I will show you, we have, because about the cycle. For a cycle, we assume that the system undergoes some different processes, then it will go back to its initial state. But for a combustion uh, cycle, actually, uh, it is not like that. In other words, we have a piston, cylinder, gas come to the system with the fuel, combustion reaction happen, then it will goes out of the system. So the working fluid actually goes out of the system. This is another problem to solve this kind of the uh, uh, problem related to this kind of the cycle, because the working fluid come to the system and go out of the system. So how we can calculate the equation for this type of the cycle, because the gas as our system come to the system then goes out of the system. How we can calculate the equation for that? You may say we can use control volume, because the mass come to the system, mass goes out of the system. But it will be still too complicated to solve in that situation. So instead of that, we can assume that however we have fuel and air to the uh, cylinder, we can assume that this is energy gained by the system. In other words, we can assume this is energy, not mass, to the system. This is another assumption. So we imagine we have Q into the system, Q out of the system. We will see this later how we can use it. So instead of air and fuel to the system, we can assume that we have Q into the system and Q out from the system. This is another thing which help us, which you can see here as well. It is mentioned. So the actual gas power cycle actually is a complex cycle. We cannot easily evaluate that. So we need to have some assumptions, but reasonable assumptions, to solve these, to manage actually, or to be able to evaluate these type of the cycles. Then we will need to follow some approximations. We call these approximations actually air standard assumptions. These assumptions are important. Without this assumption, actually, we cannot solve problem related this type of the cycle. This is what we have in actual gas power cycle, or what we have, which is for example, an internal combustion engine. We have a combustion chamber. Air and fuel come to this chamber. They react. Energy is released. Then the products will go out of the combustion chamber. You know, it is easy to understand. I think fuel from one side, air react, energy is released, and then the burned fuel and the air will go out of the system from the exhaust tailpipe. This is the actual one. You can see here it's not easy to manage. So instead of that, we can have this idealization. We can assume that we have a cycle or we have a system like this. Air comes to the system, goes off the system as our working fluid. Then heat is actually also input the system. Instead of the heat generation inside the system, we can assume this heat come to the system or thermal energy. So this is the simplification which we have. This simplification can be defined like this as air standard assumption. First of all, the working fluid is air. As I said, it is important. It enables us to use some equations and some tables to solve and find enthalpy and entropy for different states in the cycle. So the working fluid is air which continuously circulates in a closed loop and always behaves as an ideal gas. This is very important. Two, all the processes that makes up the cycle are internally reversible because I told you, especially in previous session, we need to have this assumption. It helps us to draw, especially the graph, much easier. And assumption number three, the combustion process is replaced by a heat addition process from an external source, like what you can see here. However, the combustion is happen inside the cylinder, inside the chamber, and energy is released. We can assume that heat come to the system from a heat source from the outside of the chamber, actually. And assumption number four is the exhaust process is replaced by a heat rejection process that restores the working fluid to its initial state. By this, we can have a much more simple cycle, actually. Instead of the change in the working fluid in the system, we can assume the energy of the working fluid is changing, actually. This is the standard assumption, very important. We need to have these assumptions to solve any problem related to the gas power cycle. So before you solve a problem, you need to declare these assumptions. Or otherwise, if you are not going to use this assumption, you need to declare. Because, the rest of this chapter, I will continue to solve some problems, to introduce some equations. Those equations are based on these assumptions. So we need to have these assumptions. These assumptions are called cold air standard assumptions when the working fluid is considered to be air with constant specific heat, or C, if you remember Cp and Cv. If we assume that the specific heat is constant at room temperature or 25 degrees Celsius, these standards, these assumptions are called cold air standard assumptions. You can see why we call that cold, because we assume that the specific heat of the air is constant and it is equal to 25 degree specific heat of the air at 25 degree Celsius. However, in combustion chamber, the temperature of the air as our working fluid based on our assumption is much higher than 25 degree Celsius. But according to this cold air standard assumption, we can have that. And why it is important? Later, you will see in some cases during the combustion process, especially, the temperature of the air inside the cylinder is not constant. It is changing. And to to calculate the change in the energy, it is not easy. If you remember, we had some equation to find change in the energy. For example, uh, uh, if you remember, we had delta U equal to C T2 minus T1, something like this, for example, we had. And we need to have this C. This is valid uh, only if C is constant. If it is variable as a specific heat, we cannot use this equation, or it will be too much complicated. Then, if we assume it is constant, easily we can use this equation. The other definition related to this air standard assumption is air standard cycle. Any cycle which works based on this air standard assumption is called air standard cycle. So a cycle for which the air standard assumptions are applicable is called air standard cycle. These air standard assumptions, which I introduced to you, will help us a lot to simplify the problems for the gas powered cycle. Then we can use some equations to evaluate this type of the cycle, to find its efficiency, to understand why its efficiency is low, why it is high, and where we can improve that. Now, after this introduction, let me just show you a brief video about internal combustion engine and why they are important. I think none of you uh, uh, can, you know, live actually or survive without using this type of the, devices, which we call them cars. But the most important part of the different type of the cars actually is its power source. However, nowadays, we have a new generation of the cars which they use electric. Uh, we call them electric machines actually, or EVs. But these type of the car which we are using now are invented about more than 100 years ago. These type of the engine are invented initially in 1876 by Otto. Then it was the diesel one also invented about 1880 something. So you can see these equipment, these devices are invented 100 plus years ago, but they are still reliable. They have improved a lot. They are reliable. And why they are important? Because they can provide lots of energy and power for us to run a car. You have experience and you most of you actually drive a car, so you know how much it can be powerful. It can transfer people. It can be a source of the energy to even to produce electricity. We can use internal combustion engine to produce electricity by different type of the generator. So these equipment actually are among one of the most important invention in the history. And now in a video, you will see a brief introduction about that. First of all, uh, let me know if you can, hear the video. If you cannot hear the video, what is in the video, please let me know. Can you hear the video?
Yes.
Yes,
Okay,
yes, yes.
Yes.
thank you.
Science, please! Do the words auto mechanics make you curious? Actually, it's a cinch. A car is made up of wheels, seats, fuzzy legs, a body, and an engine. The internal combustion engine. The engine works in four stages. First, a valve opens and the piston lowers, letting a mixture of fuel and air into the combustion chamber. Second, as it comes up, the piston compresses the fuel-air mixture. Third, a spark from the spark plug ignites the mixture, which pushes the piston down again. Fourth, the exhaust valve opens and as it comes up, the piston pushes the spent gases out. And the cycle starts over again. Intake, compression, combustion, exhaust, intake, compression, combustion, exhaust, intake, compression, combustion, exhaust, intake, compression. The movement of the engine is transmitted to the wheels for the drivers to light.
Okay, very short video which you have seen how an internal combustion engine works. How this type of engine actually we call them SI engine. Later I will tell you why we call them spark plug type engine actually, because we need to have a spark plug to start the combustion. Now, in this slide, I'm going to introduce some basics and important. We are not going to go to too much details about the internal combustion engine. We are going to deal with this type of the engine about their thermodynamics, how the cycle, which thermodynamic cycle we have in this equipment, how is the process, and so on. So we are not going to go to the details of internal combustion engine. We just will discuss about the thermodynamics aspect of internal combustion engines. The basic component which we can distinguish for these different type of the internal combustion engines, as you can see in this figure, are two. We have two valves: intake valves. Intake valve actually for a cylinder, which gas and air come to the piston cylinder by that valve. An exhaust valve, which after combustion, the gas, the burned fuel and gas will goes out from that valve. So we have two valves generally. It can be higher the number of the valves, which is out of the scope of this context to discuss about that. And it has a cylinder piston which can move the between two different position. It can move actually the piston, which we call them TDC as the top dead center and BDC as the bottom dead center. These two position actually, the top dead center is the position of the piston, which it forms the smallest volume in the cylinder. In other words, the maximum possible displacement of the piston closer to the cylinder head. We call this part cylinder head. So the piston when it come up, it will the space which we have inside the cylinder is only this part. This is the minimum or smallest volume in the cylinder. This position for the piston is called top dead center. We say the piston is in its top dead center, and also this is the smallest volume of the cylinder. After that, the piston will goes down actually until it reaches its bottom dead center. This position of the piston is when it forms the largest volume in the cylinder. At the top dead center, the volume inside the cylinder is this much only. But if it goes to its bottom dead center, the cylinder will be here. The volume inside the cylinder or volume of the gas inside the cylinder actually will be here. So for in top dead center we have V mean, and in bottom dead center we have V max. The distance between these two, top dead center and bottom dead center, is called a stroke, and the piston actually travels between these 2 points, and this distance is called one stroke. The other important thing about the internal combustion engine actually is the bore, which is the diameter of the piston. So diameter of the piston is called bore for a piston cylinder. And as I said, the air fuel mixture will come to the system from the intake valve, and the combustion product will go out from the system by exhaust valve. This is generally what we have in a reciprocating engine. Actually, we call that reciprocating engine because you have seen in previous slide in a video that we need different structs to run the engine. Now, in another video, actually, I'm going to show you more detail about this. Let me just play this video.
A basic lesson in the fundamentals of a four-stroke EFI gas engine may be helpful to your understanding of Mercury products. Here are the basic components of every four-stroke gas engine: a piston, a connecting rod, a crankshaft. As the piston travels up and down in the cylinder, this lateral motion is turned into a rotating motion at the crankshaft. The longer the stroke of the piston, the larger the displacement of gas and air occurs in the cylinder. To propel that piston, we need to ignite a tiny bit of gas and a whole lot of air. This creates expansion inside the cylinder. The fuel delivery system consists of an air intake manifold, valves, intake and exhaust, a fuel injector, and a spark plug. A four-stroke engine is called a four-stroke because 4 up and down motions are needed to complete the cycle. In the first stroke, the piston travels downward as the intake valve opens and a mixture of air from the atmosphere and a metered amount of gas from the electronic fuel injector enter the cylinder. This is called the intake stroke. On the second stroke, the piston travels upward, compressing the air and fuel to make a highly combustible mixture. This is called the compression stroke. At this point, the spark plug fires, sending the piston downward from the expansion of the air and gas mixture. This is the combustion stroke. The fourth stroke is the exhaust stroke. As the piston travels upward, the exhaust valve opens to release the burned air-fuel mixture. When the piston reaches the top of this stroke, the intake valve opens and the cycle begins all over again. It takes 1 up and down motion, or 2 strokes of the piston, to create 1 revolution of the crankshaft. RPMs, or revolutions per minute, is how many times the crankshaft rotates within that minute. At wide open throttle, the crankshaft may turn at 5,000 RPMs, or a dizzyingly 83 times per second. Meanwhile, the piston traveled up and down 166 times in that same second. Want to see how fast that is? Now, that's fast. Let's see it again. Amazingly, the four-stroke EFI engine does this smoothly, quietly, and reliably for years and years of operation.
Okay, you have seen actually these strokes. We have 4 different strokes in a common type of the internal combustion engine, and by these 4 strokes actually it makes a cycle to produce this power in the engine, and this is how we can use the engine to run, for example, our cars and so on. And it is reliable, as you can see, discussed also in the video. However, it is, the working condition for the engine is not that much easy operating condition actually fast movement, lots of mechanical part movement are moving, and we have friction, we have the you know high amount of temperature, but still it is reliable. It can produce energy for us, which actually is accessible, it is useful, and we can use them. And again, in this video, you have seen some new definition which are important. First of all, we call this type of the engine as a uh, four-stroke cycle engine actually, because we need to have four-stroke to create a cycle in the engine, and because of that cycle we have power. So it is important to evaluate each one of these struct, which I will discuss about that later. But first, let me introduce a characteristic of the engine, which is very important, and sometimes engines are classified actually based on this characteristic. We call that compression ratio. Compression ratio is as it comes from its name, is a ratio. It is the result of division of the Vmax, or the maximum possible uh, cylinder volume, divided by V mean or minimum uh, possible volume of the cylinder. In other words, Vmax is when the piston is in its bottom dead center, or BDC. V mean is when the piston is in its top dead center. So by this, we can, by this equation actually, we can calculate the compression ratio. Later you will see why it is important, why compression ratio is important, because it is effective on the thermal efficiency of the engine, and we will see later. These two, Vmax and Vmin, actually are described as clearance volume and displacement volume. So the minimum volume forming the cylinder when the piston is in the top dead center is called clearance volume, and the volume displaced by the piston as it moves between top dead center and bottom dead center is called displacement volume. So this is displacement volume, this is clearance volume. As I said, to find R, we need to have Vmax and Vmin, which Vmax actually is these two, the plus. We need to sum these two, the displacement and clearance, but the Vmin is only clearance. And it is important to notice, because later it may be a little problematic, that compression ratio is not about the pressure, it's about the volume. In other words, it shows how much the volume is reduced. So the compression ratio is volume ratio, and it is important later on to study the cycle. And another important characteristic of the engine, this reciprocating engine, is mean effective pressure. It is also another important characteristic of the engine, and it shows, it is we can calculate this pressure, uh, to know how much power we can get from the engine actually. So this mean effective pressure is another characteristic of the engine. It is a fictitious pressure that it acted on the piston during entire power stroke. Here in the example also you have seen that the you know the piston is moving downward during the we have four different strokes. One of them is power stroke, when the spark is ignited and the fuel is burning, energy is releasing, and it pushed down the piston. But this pressure, the pressure on the surface of the piston is not constant. You can see here the piston is moving, then its pressure, this is PV diagram for our system, which is the gas inside the piston cylinder device. You can see Vmax, this is bottom dead center. It goes down, and this cycle, is uh, formed like this. And you can see the pressure at each point of this cycle is different. Pressure at this point, pressure at this point, pressure at this point. This pressure is pressure which acting on the surface of this piston. So this mean effective pressure is defined to have an average amount of pressure which is acting on the surface of this piston. And it is useful to calculate the work, because that the force times the displacement will give us the work. So the force is nothing but the pressure times the surface area. So we need to have the pressure, but pressure is changing. So how we can have an average pressure? This average pressure is called mean effective pressure, or MEP. How we can calculate that? By this equation actually. MEP is equal to this area. However, uh, this MEP can be calculated by this equation. MEP equal to W net divided by Vmax and Vmean. And Vmax and Vmean is clear. They are dimensions. We can measure that, how much is Vmax, how much is Vmean, how much is the cylinder volume when the piston is in top dead center, when it is in bottom dead center. And W net we can calculate for the cycle. The simply W net in PV diagram is the area inside the cycle. And also we can calculate by the equations which by later we will see. We can calculate W net, and this W net, or the net work output of the engine, can be calculated. When we have W net, Vmax and Vmean, we can calculate mean effective pressure. Why it is important? Because sometimes it is also important to compare different types of the engines. Engines are produced in different sizes, in different configuration. However, the basic concept is same, but the size is different. For example, number of the cylinder is different. So this MEP will help us to compare them. So the engine with a larger value of the MEP delivers more net work per cycle, and thus perform better. You can see why MEP is important. We are interested to have an engine with higher amount of MEP. The other classification for the engines or reciprocating engine is actually based on how the combustion starts actually, or how fuel and air are mixed and start to uh, um, combustion actually. Based on that, we have two classes. We have the spark ignition internal combustion engine, and we have compression ignition, or CI engine. So we have SI and CI engine. This is important. Later on, we will call just them as SI and CI engine. And this classification depends on the combustion, how the combustion process is initiated in the cylinder. In the spark ignition engines or SI engines, we have a spark plug, a spark to start the combustion. But in compression ignition engines or CI engines, the combustion starts due to the high pressure and temperature inside the cylinder, and only fuel, when the fuel is injected actually inside the cylinder, combustion will start. About the compression ignition engines or CI engines, we will discuss in next session. In this session, we will continue our discussion about spark ignition engines. In this type of the engine actually, air fuel mixture is the combustion of air fuel mixture is initiated by a spark plug. So first of all, air and fuel, both of them together will come to the system. Here to the cylinder, air plus fuel, both of them together will come to the cylinder. So we have air fuel mixture to the system, and also we have an spark plug here to start uh, the combustion reaction actually. So this is important thing about SI engine. But as I say, in CI engine, the air fuel mixture is self-ignited due to the high temperature and pressure which we have inside the cylinder, which is topic of the next session. First, I will introduce you the Otto cycle in this session. Next session, I will introduce you diesel cycle, which Otto cycle is ideal cycle for SI engines. The type of the engine is a spark ignition engine. The cycle which is ideal for that is Otto cycle. Again, the actual cycle is complicated. We need to have some ideal cycle to evaluate this type of the cycle. For SI engine, we have Otto cycle. For CI engine, we have diesel cycle. So you can see how we can have two different cycles to evaluate these type of the engine. Now let's see the main difference between SI and CI engines. Next, I will introduce you the Otto cycle actually.
Gasoline and diesel engines are the two most commonly used internal combustion engines. Even though their operations seem similar, they have some interesting differences, and each has advantages over the other. This video is aimed at exploring these differences and advantages from a scientific point of view. Both engines have the basic four strokes: intake, compression, power, and exhaust. There are differences between the two engines due to the difference between the way fuels burn. Gasoline readily evaporates, so it gets mixed with the air efficiently. As a result, just a spark is sufficient to produce smooth combustion in a well-pre-mixed gasoline engine. On the other hand, diesel does not properly mix with air. However, if atomized diesel is sprayed into high-temperature air, spontaneous combustion will occur. This means that in gasoline engines, the fuel and air should be pre-mixed. While in diesel engines, mixing happens only during the combustion. This is why diesel engines use a fuel injector, while gasoline engines use a spark plug. You might have noticed that gasoline engines are less noisy and vibrate less compared to diesel engines. This is because the combustion process in a premixed mixture is smooth and propagates well. But in a diesel engine, the combustion could begin anywhere in the combustion chamber, and it turns out to be an uncontrolled process. For this reason, to reduce the excessive vibration and noise problem, diesel engines require a more rugged structural design than gasoline engines. This is why gasoline engines are always preferable for lightweight applications. Since the diesel engine is compressing only the air, it can achieve a good compression ratio without risk of self-ignition. But in a premixed gasoline engine, Such a high compression ratio is not possible. The higher the compression ratio, the better the efficiency of the cycle. This is the reason why diesel engines have better fuel economy as compared to gasoline engines. An interesting question many people wonder is, what if I put gasoline into a diesel engine or vice versa? Diesel in a gasoline engine will not even cause firing. The reason is simple. Diesel is less volatile and will not mix with the air properly, and the sparking will not initiate any combustion. On the other hand, if you put gasoline in a diesel engine, you are spraying a highly volatile fuel into a chamber of highly compressed and hot air. This will lead to detonations rather than smooth combustion. Eventually, the engine components will get damaged. So that's a big no for gasoline in a diesel engine. Thank you for watching the
Okay, in this video, you have seen what is the main differences actually between the CI and SI engines, and also some other important information which I will also discuss about them later, how the compression ratio is effective and the thermal efficiency of the engines, and also how is the the fuel type or engine type is effective on the auto ignition inside the cylinder. I will discuss about that. First, let me just discuss about the cycle which we have in the engine. You have already saw in this. You have already seen in these videos in most of the videos which you have watched up to now in this session. You have seen that we have four strokes in the engine to produce the power in the engine actually. You haven't seen the cycle for that actually, but you know we have four different strokes in each cycle. Now we are going to consider or to see how is the PV diagram for this cycle. So we have an SI engine, as you can see here. We have an SI engine. We are going to show these four different strokes for the engine and how pressure and volume change inside the cylinder during these four strokes. The first one, the upper one, this PV diagram actually is for the actual cycle which we have in a spark ignition engine. So first of all, the uh, process, the cycle starts from this stage. The piston is in its top dead center. It starts to going down toward its bottom dead center. We call this stroke as intake stroke, and during that, air fuel mixture will come to the system. Now, let's see how we can uh, draw the how is the pressure and volume during this process. First of all, volume is increasing during this process. It is expansion process actually, and also pressure will need to reduce. Okay, so you can see in the PV diagram first here, intake valves open due to this opening of the valve. Pressure is drops. Initially the pressure when the piston is in its top dead center, pressure inside the cylinder is equal to pressure of outside of the cylinder, which is atmosphere pressure. So you can see here initially uh, when valve opens at the beginning is a little higher than the atmosphere pressure, but due to the suction of the air and fuel actually by piston, the pressure will drop and it will go a little lower than the atmospheric pressure. Then we will have this intake process actually. It starts from this point to this point actually. Okay, so pressure you can see here is almost constant. because this will goes down gradually the piston, and air fuel mixture come to the cylinder gradually. So we can say that pressure during this process, uh, uh, the intake stroke actually is like this. It is almost constant beginning. Then when it starts to rotate and go up, actually this is intake, we need to go to the compression. So after the suction happened, the intake stroke finished, the piston start to go up. The intake valve is closed, exhaust valve is closed. Air fuel mixture actually start to compress. We have this process here. The pressure is increased, volume is decreased. Volume is decreased. You can see here, volume is decreasing, and pressure is increasing. Is process is compression stroke. After that, we will have this process, the stroke, which is power expansion. After this, actually before this piston reached its top dead center, due to ignition, the uh, combustion reaction starts, and it's release lots of energy, and this energy actually, will increase the pressure inside the cylinder. So uh, this is the combustion stroke actually, or power stroke actually. Initially, its temperature will goes too high, then pressure also will increase too much. So you can see here, ignition will happen before piston reach its top dead center, because the fuel combustion also takes time. uh, then we need to have some time, some just few milliseconds to for expansion, for the to have the combustion in entire cylinder. So because of that, we put ignition before piston reached its top dead center. But the maximum pressure which we have in the cylinder, it's actually at the beginning of our power expansion stroke, or we are interested to have this, because however the ignition is before the top dead center, before piston reach top dead center, but we don't want to have the maximum pressure in that point, because it will, if piston is going up, we have expansion and combustion reaction, it will try to push down the piston. But because as I said, it takes time to whole fuel and air react inside the piston cylinder device, then we have time. The piston will goes up, then while it starts to coming out, the whole energy, or whole energy which come from the combustion, will release and will push down the piston. This is displays the maximum pressure which we have. Then we have this expansion process or power stroke. So this is the expansion process. You can see here, during this expansion process, power. This is only a stroke which we have power production actually. Power is produced. The energy which comes from the combustion of air and fuel will push down the piston. You can see here the pressure will drop due to the expansion, and the volume is increased also due to the expansion. Due to this, you can see the volume will decrease during this process. After this, we will have another stroke, which we need that stroke to uh, take out the burned or exhaust gases actually. So when after the piston reach its bottom dead center, it will start going up, and exhaust valve will open. Then this when piston is going up from bottom dead center toward its top dead center, its exhaust gases will go out from the piston. This process is also shown on the PV diagram like this. You can see here the pressure continue to reduce the uh, to continue to reduce inside the cylinder, and when the exhaust valve opens and piston is going up, pressure is almost constant during this from this point to this point, this state actually, because without any resistance, the gas can go out from the cylinder. So the pressure will be constant, but the volume will reduce to go to its initial state. By this graph, you can see how these four strokes are happening inside the cylinder and how we can illustrate these four different strokes in the cylinder. And you can see here the actual cycle. As I said, it is a little, or not actually a little, it is complicated, it, uh, how we can calculate the change in the energy or the working fluid which we have air fuel mixture for this cycle by this graph. It is not that much easy actually, because you can see it is curves. We cannot calculate some parts of that. So Otto and a scientist suggested another cycle, an ideal cycle, which is called Otto cycle, to illustrate PV diagram for SI engine, for combustion in a SI engines. As you can see in this PV diagram, it is assumed that we have a constant volume for in this state from state uh, 4 to 1 actually, uh, which is the exhaust or the exhaust stroke. And also it is assumed that we have another constant volume process from state 2 to state 3, which is the power stroke actually. It is assumed that the piston is constant place, but the energy come to the system and its pressure is increased. So you can see how this cycle, the actual cycle, is simplified to this cycle. In other words, instead of here the volume is changing, but it is assumed that the volume is constant during the expansion. During the exhaust stroke, we have assumed that we have two constant volume process. You can see here also this process. The intake stroke is assumed that we have a constant volume process, but it is a heat rejection process. And for the exhaust stroke, it is assumed that we have an isentropic expansion. For the heat, for the power expansion, it is assumed that again we have a constant volume process, heat addition, actually constant volume heat addition process, and for compression process, it is assumed that we have an isentropic expansion process. In other words, it is assumed that we don't have any heat transfer during that process. So with some simplification, we can have this PV diagram as an Otto diagram actually for SI engine. You can see here how different strokes are illustrated in this cycle. Instead of movement of piston and production of the power during this cycle, for example, which is power expansion, it is assumed the piston is in constant place, but the energy is given to the system, Q in. So constant volume, but heat addition to the system. This is just our assumption. So then we can have this graph, which we call that Otto cycle. Uh, as I said, this cycle includes two isentropic process, one of them compression, the other one expansion, and two constant volume process. One of them is constant volume heat addition, the other one constant volume heat rejection. And in this graph also you can see TS diagram. Here is PV diagram for this Otto cycle. Here is TS diagram for Otto cycle. Again, you can see constant I entropy or isentropic process, constant volume process, which we have heat addition and heat rejection. This cycle actually is created based on our assumption which we have. And as I said, it is hard to analyze this system thermodynamically, the cycle, the actual cycle. So we can use the air standard assumption for this cycle. Then the resulting cycle is Otto cycle. And please notice, still the cycle which we have Otto cycle is more or less similar to the actual cycle. So this cycle, the Otto cycle, will help us to evaluate the combustion cycle or combustion reaction in the SI engine. It will cause some errors in our calculation because we have some assumptions, but it is helpful to evaluate that because without this assumption, it is not that much easy to evaluate that. This cycle is very important. Up to now, what I told you actually was about the four stroke cycles actually, and we had intake, exhaust, expansion or power, and compression strokes actually. But we can have also two stroke engines. In other words, we have some engines which instead of four stroke, a cycle will complete in just one cycle. In other words, in just one revolution of the camshaft actually, crank uh, crank case actually, it's happened crankshaft actually, it happened the cycle will complete just in two revolutions for stroke cycles. In one revolution for two stroke cycle it happens. If you notice here, we need to have two revolution of the crankshaft or for movement of the piston, for travel of the piston to complete a cycle. But we can have also um, engine and spark ignition engine like what you can see here, which the cycle just finished in one revolution, a revolution of the crankshaft. Still, for this kind of the engine, we have both uh, all of those, intake, the expansion, ignition, and also the compression. But they happen together. They happen together. If I want to give you more detail, I will show you a video about the two-stroke uh, engines. But just it is important to know that this type of the engine, because we just need two stroke to complete a cycle, are the efficiency is higher. We can have a smaller engine, the engine which we have in the some small equipment like the some sprayers which use small engines. The engine, or even for some kind of the bikes, the engine is very small. This is because that engine is two-stroke engine. The combustion and the exhaust stroke actually happen together, and compression and power actually come together. And in a video you can see more detail about that, how it happens actually. And as I said, it is important to know that these engines are, the efficiency for this type of engine is higher because we have for uh, each revolution we have one power stroke. So the power generally can we say that the power for two-stroke engines is double compared to the four-stroke engines, because in four-stroke engines we need to have two revolution to power to have one power stroke. But for the two-stroke engines, in just one revolution, we have one power stroke. So let's see in a video explanation about this kind of the engine actually, which you can, I think, understand it much easier.
There are now two types of engine available in PWCs, two-stroke and four-stroke. These names are derived from the number of strokes that the pistons take to complete a cycle. For example, a four-stroke engine takes 4 piston movements to complete its engine cycle. The piston lowers for the intake stroke, drawing in the air-fuel mixture, raises for the compression stroke. The air-fuel mixture is ignited for the power stroke, forcing the piston down. And finally, raised for the exhaust stroke, forcing the exhaust out of the engine. The cycle then repeats over and over, turning the crankshaft, which is connected to the impeller, which drives the craft forward. A two-stroke engine is designed to accomplish its complete cycle in just 2 strokes. During its power stroke, the ignited air-fuel charge forces the piston down until it reaches an opening on the side of the cylinder called the exhaust port. As the piston continues down, it pressurizes the air and fuel mixture under the piston that was drawn into the crankcase during the previous compression stroke. An intake transfer port is exposed, allowing the pressurized air and fuel into the cylinder. Finally, as the crankshaft continues to turn, the piston rises, closing off the intake and exhaust ports and compressing the air-fuel charge inside the cylinder. The rising piston also sucks in the next air-fuel charge under it into the crankcase from the carburetors. The compressed charge is ignited by the spark plug, repeating the cycle. The biggest advantages of two-stroke engines are lightweight and simplicity in parts. The engine itself weighs significantly less than a four-stroke with equal power output, and there are anywhere from 30 to 50% fewer moving parts in a two-stroke engine compared to a four-stroke. It is also much easier to clear out a two-stroke engine that has been swamped with water. The biggest disadvantages are increased fuel consumption and elevated hydrocarbon emissions from its exhaust compared to a four-stroke. Because a two-stroke has the intake and exhaust open at the same time, some of the fresh air fuel charge passes through the cylinder and out the exhaust port without ever being burned. Because of this and other factors, two-stroke engines have higher unburned hydrocarbon output in their exhaust than comparable four-strokes. There are significant exceptions to this, particularly with engines that use direct injection technology or
the rest of the video actually is out of the scope of especially today's session. Discuss about how we can modify the two-stroke engines to have, because you know these two-stroke engines are very interesting. They can provide more energy, you can see, but the problem is their emission. So different methods have been proposed to reduce the emission of this type of the engine, because as you can see, as you have seen in the video, some a few amount of the fuel may not burn during the combustion process, or even some the some of the exhaust gas cannot go out of the cylinder, still be inside the cylinder during the next round of the combustion. So the emission is the main problem for this kind of the engine. The power is high, power to volume actually, because the volume can be lower, but the power can be higher than the two four strokes. So we to have same amount of the power, we can have a smaller engine, two-stroke engine, but the emission is the main problem. So different methods because we is proposed to reduce the emission of this kind of the engine, because they are interesting. The power output is higher than four-stroke, but the emission is higher. So different methods have been proposed to reduce their emission, to enable us to use this kind of the engine as well for different type of the cars, especially for the small one. Okay, up to now you have seen in previous slide what is Otto cycle, how it is developed for the SI engines, and we have seen the PV diagram for this Otto cycle. You know what is important up to now, and you need to know is you need to memorize this PV diagram for Otto cycle. This is Otto cycle. Always you need to know this cycle, like Carnot cycle, which I told you in the first session, I think, that you need to draw that. Otto cycle is also like this, and it is a general form of the Otto cycle. You need to always know this. Two isentropic process, two constant volume process. You need to always know how to draw this graph. It is helpful, and now we are going to see how we can evaluate this cycle based on the laws of the thermodynamics. First of all, you know that the Otto cycle which we have here is a closed system, and by the air assumption, this closed system is developed actually. If we ignore the change in the kinetic and potential energy, you know from thermodynamics that we can write this equation in unit mass basis actually for the energy balance in the system. This is delta Q plus delta W equal to delta E. And as you know, delta E is equal to delta H, delta K plus delta P. We ignore delta K, we ignore delta P. Then the change in the energy of the system will be only equal to the change in the enthalpy of the system. In other words, for this cycle, we can write this equation. Q in minus Q out, which is changing the energy of the system due to the heat transfer to or from the system, plus W in minus W out, which is the power, the work which is done under by the system or on the system, and this is the change in the energy of the system. This comes from the first law of thermodynamics, or this is energy balance. Any name which you can, which you are familiar with that, we can call that actually. So this is energy balance or equation for our cycle or Otto cycle, which is developed based on the first law of thermodynamics. And you know from the thermodynamics for Q in, which we have in this cycle, which is an constant volume process actually. The Q in can be calculated by this equation, U3 minus U2. In other words, internal energy just only happen during this process. You know, the change in the energy of the system may change due to the change in the internal energy or the other type of the energy. Other type of the energy like kinetic and potential we assume are zero, and also the volume is constant during this process. So the Q in which come to the system only change internal energy of the system. Or you know from thermodynamics that for a constant volume process, we have this equation Q in equal to U3. In this process we have Q in U3 internal energy at state 3 minus internal energy at state 2. Q in equal to U3 minus U2. And from thermodynamics, you know that we can write this equation. Why? I told you, because we have air standard assumptions. We assume working fluid is air here. And for air as an ideal gas, we can write this equation U3 minus U2 equal to, this is CV or specific heat, constant volume specific heat actually. Here we have a constant volume process, then we can have CV, but which CV? Based on our assumption, we can refer to table and simply find this CV for air during this heat addition process. So Q in can be calculated by this equation. Q out, which is in the the exhaust extract actually, or from state 4 to 1, again, we have a constant volume process. Simply Q out of the system will be equal to the change in the internal energy of the system during that process, or U4 minus U1. Again, air is an ideal gas here, then we can write Cv times T4 minus T1. Temperature at state 4 minus temperature at state 1. So we have these two equations to calculate Q in and Q out of the system. Now, again, from thermodynamics, you know that thermal efficiency of any type of the cycle is equal to W net divided by Q in, or 1 minus Q out Q in. In the previous session also I reviewed, we call this to you, that thermal efficiency of any cycle can be calculated by the equation for a heat engine, which internal combustion engine also is a heat engine. And thermal efficiency for the Otto cycle, how it can be, or it may be, the W net divided by Q in equal to 1 minus Q out by Q in. This is general equation. But here we have calculated Q out and Q in simply by substitution of Q out from this equation, Q in from this equation. Here we will have 1 minus T4 minus T1 divided by T3 minus T2, because Cv is crossed out from the numerator and denominator. So Cv will cross out and we will have this equation. By some restructuring of the equation, we can have this new equation 1 minus T1. We just bring out T1 from this. If T1 is multiplied by this, we again have this equation. So we bring out T1 from this equation, we bring out T2 from this equation. It is useful. Why? Because now we are going to introduce a new characteristics, new property or parameter, which is developed based on the temperature ratio. But before that, we need to introduce, before that, we need to recall the compression ratio. If you remember, for compression ratio or R, we had this equation, V max divided by V min. But here you can see in our cycle, V max is here, bottom dead center, and V min is this state. In state 2 and state 3, we have V min. So in other words, we can, instead of V max, write V1, volume at this state. Instead of V min, we can write V2, volume at state 2. So compression ratio for this cycle is equal to V1 divided by V2, or in terms of the specific volume, which is divided by mass. Because mass is constant during this cycle, we assume we have a closed system, then it will be V1 divided by V2. These V1 and V2, based on the temperature and pressure which we have, you can find that from the different tables which we have for air as an ideal gas. So V1 and V2 are specific volume. This comes from the compression ratio, which I have already introduced to you. Now, here we have T1 divided by T2. So T1 divided by T2, if you remember, we had this equation. If you go back to thermodynamics in chapter 3, I think I have introduced this equation to you. T1 divided by T2 is equal to V2 divided by V1 power K minus 1, which this K is a specific its ratio, or in other words, it's Cp divided by Cv. This specific ratio comes from thermodynamics. I'm not going to again just go to its details, but we have this equation actually, which shows, it is valid for ideal gases, for which A is ideal gases here. This now again you can see why we need those assumptions. So T1 divided by T2 equal to V2 divided by V1 power K minus 1. This comes from thermodynamics, and also the rest of that V3 and V4 also, you can see here V2 is equal to V3. So instead of V2, we can write V3. V1 is equal to V4. You can see here again. So this equation also is valid with 3 divided by v 4 power k minus 1, and you can also substitute, this equation is for T4 and T3. So we can have this equation actually, which is based on our knowledge from thermodynamics. If we substitute, this with 3 divided by 4 power k minus 1 instead of this equation, this ratio which we have here, instead of T1 divided by T2, if we write this instead of T4 divided by, T1 and T3 divided by T2, by some manipulation, if we write this uh, equation actually, finally, what is important for us as well is this equation, thermal efficiency of Otto cycle based on the compression ratio and a specific heat ratio. This is a general equation, and actually an important equation which we need to have this equation. We need to use this equation sometimes to calculate thermal efficiency. And it is also helpful to understand how the thermal efficiency of Otto cycle change with the compression ratio, because and also the specific heat ratio, because you know that the compression ratio is under our control. We can design a cylinder, piston, the size can be different, we can compress it more, that we can determine the displacement of the piston, so we can change the compression ratio, and it is effective on the thermal efficiency of the cycle. By this equation, we can see how it is effective on the Otto cycle thermal efficiency. In this graph, you can see how it is effective. You can see here, as much as compression ratio is increased, you can see here as well, when R is increased, this will reduce, R increase, the whole of this will reduce. Then uh, actually the whole equation here, this part will reduce and thermal efficiency will increase. This is what you can see here. By increasing the compression ratio, the thermal efficiency of Otto cycle is increased. The compression ratio is a number, and you can see here 2, 4, and so on. But generally, the compression ratio which we have for compression for spark ignition engine is between 8 to 11 or 12. Actually, this is a typical compression ratio for gasoline engine. Why we, based on this reason, you can see here, as much as we increase the compression ratio, the thermal efficiency of the Otto cycle will increase. Why we just use why the compression ratio for this type of engine is between these two values, 8 to 11, for example, because of the problem of auto ignition. If the compression ratio increase a lot, ignition happen without, the spark plug, which is, it is uncontrolled combustion, which is not favorable. Sometimes will reduce the efficiency, and sometimes it, it's a start to, it cause a knock fundamental, which I will introduce to you. We call that engine knock, which is due to the premature ignition. As I said, ignition starts simultaneously because of the high compression and temperature, and this ignition happens in different places in the cylinder, and it is not started just from one point, then expand to whole cylinder and push the piston downward. It just start in different places, and these different combustion region actually, they may cause some different source of the energy. They may impact to each other and produce a vibration in the engine or engine knock. We call that engine knock actually. So this is the typical range for compression ratio of the Otto cycle. How about the effect of the specific heat ratio? You can see, as much as the specific heat ratio is higher, or K, Also, even based on this equation, you can find the reason. As much as the K is increased, the thermal efficiency is higher. But to increase K also, or a specific heat ratio, if you notice here, the equation which we have for a specific heat ratio, Cp divided by Cv, it means it is a characteristic of the fluid, the property of the fluid. In other words, we need to change the temperature of the working fluid or the air, which it is dependent on the material which cylinder and engine is produced by those material, and it depends on the maximum temperature which cylinder can resist. So also for K, we cannot increase it too much, and but the higher uh, K actually is more desirable. But generally, the K which we have is equal to 1.4. Why? Because this is the specific heat ratio for the air in the room temperature. In other words, the temperature which we have in the environment is a limitation for the working of the engine, and the specific heat of the air depends on the temperature of the surrounding. So usually K will be 1.4 for different type of the engine. This is another limitation which we have, or another property which we usually have. In many examples, we just use K equal to 1.4 to use this equation to calculate the efficiency of the Otto cycle. So now you can see how we can calculate thermal efficiency of the Otto cycle for gasoline engine or SI engine. Then how much can be actually the thermal efficiency of this type of the engines or heat engines? The efficiency, the common efficiency which we have for this kind of engine nowadays, even for the most, uh, the efficient one, is between 24 to 30%. In other words, only 24, 25 actually, or 30% of the useful energy which comes from the fuel is converted to the useful work by this kind of the engine. Later, we will compare the thermal efficiency of the Otto cycle or the gasoline engine with diesel engine as well. Here, I just review the engine knock what it happens because it is a limitation. As an engineer, you need to know why we cannot increase the efficiency of the cycle by increasing the compression ratio to higher values, higher than 11 and so on. One thing which most of the scientists nowadays are working on that is to increase the compression ratio without increasing the engine knock actually. Engine knock comes due to the premature ignition actually, or auto ignition, and it is a bad thing actually about the engine. We call these result which come from the auto ignition as the engine knock, and it causes lower performance, and also it causes the engine damage because it causes vibration of the engine, and the high compression ratio is limited due to this engine knock actually, and it is called the upper limit of the compression ratio which we can have for an engine actually. Unfortunately, we don't have time to go through this example. Next session, we will solve an example for Otto cycle. We will see how we can calculate the thermal efficiency of the cycle and also other properties for Otto cycle for SI engine, and you will know more about this equation and thermodynamics aspect of the Otto cycle. By this, we reach end of today's session.